Hi guys, this was supposed to be a quick video to show you how to make a shift register on the board, and it's written in VHDL. It takes a long time because I managed to make some mistakes, but I left it as it is, and I hope you enjoy it. Okay guys, let's try to do it. I'll create a new project. Next, I'll make a directory here called, actually I'm going to put it in a special place. Linux project. I'm going to make a directory called tutorials. Why do you make a directory here? Tutorials. Okay. And we'll call it shift register. Okay. Okay, so it's an RTL project. Create file. Yeah, let's create file. VHDL. We'll call it shift register. Shift reg. In the local, okay. Next, constraints file, create file. Okay, we'll call it shift reg xdc. Okay, now this is going to be empty. Obviously, both of them are going to be empty. Now the FPGA that we use family is Spartan 7. The part is package. I think this is the package, and it's a 25-1 I think. Actually, what's the device? Hold on. -2. Okay, -2. Okay. Finished. Now we can define here the pins for our file. So let's try that. So I want a clock pin. Sorry, click here. Clock. Obviously, it's an input. Now I want a reset. It's an input. And what else? I want next LEDs. Actually, what I'm going to do, I'm just going to have a quick look in our constraints file. Now you can download the constraints file from the blog page or from our website. Where is the constraints file? I think I have it here somewhere. Yeah. So why I'm doing this, I'm actually looking in the constraints file to see how the LEDs are actually named. LED, and from 0 to 7. Okay. So we'll call it LED, which is an output, and it's a bus from 7 to 0. Okay. So this thing has created a source file where it's defining the entity, and it's empty, right? Not much. So and the constraints file, obviously it's empty. So I'm going to take the constraints file that I have from the website. I'm going to select all, Control C, and Control C, close this, and just paste it here. Save. Now there are a bunch of things here that we are not going to use, but the LEDs position and the clock, they are in the right place, so they are defined. So the constraints file is just defining where the pins are. So, and we have certain pins going to certain things on the board. So it's more like a image of where the pins on the board, where they go. Obviously, this is different from board to board. Okay, so we have this. So this is an empty file. Now, the quickest way to implement a shift register is actually, you have here this facility. It looks like a bulb. It's called language templates. So what we do here, we just go, or we can code by hand. I'll go the easy way. So you go here, VHDL, synthesis constructs. I'll make a separate video just to explain what means synthesizable mean and non-synthesizable. And you have here coding examples, right? And you search here, blah, 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 probably shift register. Okay, shift register. Example code. So you have here a shift register example. Now, I don't like it. I don't like it. It's kind of hard to understand how it works. Let's try another one. Simple shift. This is actually nicer. Okay, so let's copy and paste this. Obviously, we need to change a few things. So we'll put it here. So our code is going to be here between begin and end. Now, I'm not going to teach VHDL here, so I'm just going to, so here, this is called the sensitivity list. So it's, I'll put the clock here. So sensitivity list contains all the signals which, when they change, this process is going to execute. Now, this is a interesting representation, an interesting declaration of how we define the event. Sorry, I think those brackets are not here. Right? And this is our signal, that our shift register that we want. So I'm going to just define here, I'm going to declare signal shift register. Now you can put whatever name you want here. There are some restrictions, but it's a standard. This is the type. So now I'm defining the type of this shift register. It's a standard vector, standard logic vector. I'm just going to copy here because I'm lazy. Right, so a standard logic vector, and I'm giving here the size of this. So it has 8 bits, from 7 down to 0. So it's a vector of 8 bits, right? Now, what we declared here is just like a placeholder. They're basically wires. There is nothing. It's just a vector which is holding those bits. The moment we put this fella in here, so first of all, let's see what this code means. I'm just going to erase this. I'm going to erase everything inside. Right? So we have here if clock is rising, basically saying this, if there is an event and the clock is getting 1, which means it was 0 before. So if you have a rising edge of the clock, do what? So we'll say here, if reset equals 1, so if the reset is on, then load this register with value, and I'm going to put in binary here, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 1. So I'm going to initialize the register with this value. Why I initialize with this value? Because I want to see a 1 going from LSB to MSB. Okay, so this is happening if the reset is 1. Now what is happening if it's not 1? Else? I want this shift register to move the bits by 1 position, right? So I'm saying shift register equal. So this is, I'm going to make it explicitly. So I'm going to write 7 down to 0. If I don't write 7 down to 0, it still means the whole shift register, which is 7 down to 0. So, but I'm writing explicitly because it's easier to understand. So what I want this in this shift register here at the beginning of the shift register to take the MSB and come back and plug it into the LSB. So it's basically a shift register which is moving, for every clock is moving the data. but in the same time it's taking the bit which was about to drop off out of the register and bring it back to the input of the register. So what we say here, I want to load this with, I'm going to write the same thing here, Control C, but I'm going to say 6 to 0, so which basically means that bit number 6 is going to become bit number 7, bit number, okay, but obviously here we don't have 8 bits, so we have 8 bits here, we don't have 8 bits here, we have only 7, so we need to feed another bit, which is the bit which was about to fall off. So we are saying here concatenate with shift register bit number 7. So we bring bit number 7. Now, how those bits they get assigned? They get assigned positionally. So this is bit 7, with the MSB of this shift register. Here the MSB is actually bit 6 down to 0, and the LSB is this bit. So you need to, basically, those 8 bits, they are going to become, when the clock is rising, they are going to become this. So 6 goes to 7, 5 goes to 6, and so on, and 7, the former 7 goes to bit 0, which is okay. So okay, so all good except one thing. We don't, so we have an if here, we have an if here, which is closing with this. It doesn't matter if they're aligned. So in VHDL, it doesn't matter if those are. It's not like Python, all right? But I'm going to put them like this so we can actually see them better. So here I need to close the other if. So and if. Yeah, it's a bit annoying, this VHDL. Now, we need to assign the output here. So right now we have just an internal shift register, which is going to move those bits back, but we don't see anything. So we need to bring it to the LEDs. So we need to make a final assignment here, LEDs. Control C. LEDs, they are going to be assigned with the shift register down to 0. Okay. Now, one thing is our reset is not defined anywhere. So in this XDC, there is no reset. So what I'm going to do, I'm just going to use the first switch. Or no, I'm going to use SW2, which is Mark II on the board, which is this one. So I'm going to replace this name with reset. So now reset is going to go to this. Okay, save. Now, save. We have here, we should have a green bullet if everything is fine. Obviously, not everything is fine. Yeah, we have a colon missing here. When everything is fine, you should see this green, which means the syntax is okay. It doesn't mean functionally is okay. So let's just go one step and synthesize. There are no HDL sources. What is he trying to tell me? Save. Okay. Now, we go and we synthesize. Just synthesize. So why do I want just to synthesize? Because you can open the synthesized design. Let's call it design. Very precious. And it will show a schematic representation of this design. So, yeah, it's running here. You can see in the top corner. Top right corner, and you can see it here as well, and should be fairly quick. It's going to pop, yeah, so open synthesize design. Okay, let's open the synthesize design, and now we can actually see, okay, there are some warnings here because of our constraints file, which is very, very verbose, let's say. So this is what, actually this is too early now to see what is going on the device because we didn't get that far. But let's open here, when we open the synthesized, we can actually see a schematic representation of this schematic. So this is what we have. We have the outputs, the LEDs, and we have those flip-flops which they cascade one into another, and the clock coming in and the reset, right? So this is what the synthesizer understood from our code. Okay, so I'll close this synthesized design and I'll go the next step, implementation. So synthesis is more like compilation in the software land. So it takes your VHDL code and it's trying to understand the functionality and is breaking down everything in flip-flops and gates and muxes and other stuff. But it's basically trying to map everything to combinatorial logic and to sequential logic. Sequential logic means registers, combinatorial means gates. Okay. Now what it does now in the implementation is mapping those synthesized resources to resources which they actually exist on the device. We say generate bitstream. Okay. And I hope it works out of the box and I don't have any hiccups because I just wrote this from scratch. Now there are a bunch of constraints which they are not defined and it might scream. We'll see in a second. It's writing bitstream. Okay, open hardware manager, open target. I might have put the reset the other way around, so we might need to press the reset in order for this to work. But we'll find in a sec. We'll find out in a second. Program device. Shift. Okay, it's pointing in the right place. Program. And it does nothing. I'll show you with the camera. So it's okay. It's kind of stuck. Let me see. What am I doing here? I need to go that way. Alright, so those are the LEDs. So I'm going to press SW1 and I guess this is going to release the reset. Yeah, it does. Do you know what happens? Actually, I'm going to go closer. You see, those LEDs actually, they're very, very dim. I'm not sure if you can see when I press the button. What is happening is actually it goes very, 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 very fast. So why is going very fast? Because this clock is 100 megs. Of course it goes fast, right? So the clock that is feeding our shift register, imagine that there are 100,000 clock cycles per second. So it's going so fast that we can't see it that it's moving, right? So what we do here? Well, let's divide the clock. So let's make the clock a little bit slower. So how we do that? First of all, we can do it in two ways. We can divide the clock, which is probably the best. So how do we divide the clock? Okay, we'll make another, we'll call it here counter. Signal counter. We'll make a counter to divide the clock. And we'll make it how big? My guess is that it probably needs about 22 bits to have something visible. So don't worry if you don't understand those things out of the straight out of the box. So I'm going to put here a counter, and again I'm too lazy, so I go here counter, counters, binary, doesn't matter, up counter, again doesn't matter, simple counter. Okay, this is our counter, and I'm going to put it here. So I say use clock and begin clock 1. So this is actually, I'm going to show you something how you can actually write this much easier. You can go rising edge of clock. This is another, it's an elegant way of writing this. It's the same thing, has exactly the same functionality. Okay, and now the count. The count, how is it called? The counter is called counter. So we say counter. Here's counter +1. Okay, if I go now, rising edge of clock, if counter. Okay, what's the problem here? Oh, there was an if here. Okay, So we have this counter. Now, this is an interesting one. So you see here is actually complaining that the character, the plus character, doesn't know what's this plus character. So why is this happening? If you go back here and you go counters, I think because there is a library, he needs a library in order to recognize that plus sign. And I think that library is numerical. I'm not sure. I'll give it a go. No. Well, I'm too lazy. Hold on. What am I missing here? Oh. Okay. Oh, yeah. This is what I'm. So this was actually defined as unsigned. You see? So it's not as it's, and why? Because this is actually invoking the numeric library, and we need to define this as unsigned. Why? Because the unsigned library defines how to add a bit. So we need to change this counter to unsigned here. Unsigned. I think. Yeah, you see, all good here. Now, what we want when this counter rolls over, so let's say when it becomes FFFF or 0, let's say 0, to create a signal which is going to add a shift, to shift a bit. So we need to put here the combinatorial logic. Let's call it enable. Is made of, this is combinatorial, what I'm, okay, I need to define the enable, obviously. So signal enable is standard logic, which is just a bit. Okay, and we say this is, enable is 0, or 1, is 1. On counter equals, we have 23s of zeros. Okay, I'm not going to write 23s of zeros. I'm going to write others. This is a way of saying all the bits in this thing, they are 0. So this is going to become 1 when the counter is 0, else it's going to be 0. So this is a way of creating this enable signal when the counter rolls over. When all the bits in this counter they become 0, bang, it's going to be enable. So we need to put here if reset is doing that. If reset is 1 and enable. Actually, do you know what? I'm going to take this reset out of the clock process. Control X. So I'm going to make a. This is called a asynchronous reset. So it's basically, this means that if reset doesn't care about the clock. Basically, this is what it means. So when reset is, so I'm going to Control X. If reset is 1, it's going to do this. Else. Now it's looking to the clock, and I'm going to write clock in a nice way, like above. Rising edge of clock. Okay, so when the rising edge of clock is and actually not here, we'll put if, how we call enable equals 1, then count, then shift, sorry. Okay. If we set else, okay, if and we have another if here that we need to close, and if, let's hope we if we set then, so if we set, okay, it's green. So what we did here, we divided the clock by 33 bits, which is what, very large number, by a million by 4 millions, I think. And then we created this enable signal. So every few million cycles, we get this enable signal, and only then we shift. So hopefully we'll get something more visible now. So save, create bitstream. So we divided the clock, we created a counter to divide the clock, and that counter is giving an enable signal, which is very, very, it happens every few, oh, synthesis failed, what's wrong with it? Without constraining context. What is this? Could not evaluate expression others. Oh, it doesn't like this. Why? I'm going to write here 24 bits. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Those are 16. 1, 2, 3, 4. 20. 21, 22, 23. Well, I hope he's happy now. I'm not sure why it didn't work, to be honest, but now I could have done something else here. I could have just put it 24 bits and just put a hex representation here, which is way more compact. Well, look. Or we can just put some arbitrary number. It doesn't matter because it's going to match only one every so many cycles. But anyway, let's see if everything is good here. Synthesis happening. Now if it's throwing an error, I'm going to make a fool of myself. But I'm prepared to do that. This has taken too long anyway. Initializing design. Okay, so the synthesis is over. Come on. Route design. Okay. Now I need a better way to put a camera here, so I'm going to take this. I have a very short cable. Open implement, generate memory, no, cancel. A program, bang, boom. Can you see anything? Yeah, I think you do. Now I'm going to press. Look, it's working, it's slower, we can see it. Now the reset is the other way around, so I need to press it actually to work. When I release it, it stops. So what we are going to do is let's invert the reset. So here where we have the reset, where is it? If reset is 1, if reset is 0. Okay, and save and redo all this. I'm going to take another 2 minutes. So I'm going to zip this this whole design and I'm going to put it on the blog, so you can download and you can play with it and you can try to understand. Before I do that, what I'm going to modify here. I'm going to put here 23, which this equals that there are 24 bits, and having 24 bits, it means I can represent this in hex because it's a odd number of 4 bits. So I'll say here this is hex number, and I go 1, 2, 3, 4. Those are 16 bits, 20 bits, 24. So I can break this. What the What? So, the first hex character, the second, third, fourth, fifth. That is what? 16 bits and another one. That should be fine now. So it's a more compact. When I put a hex in front, it means that is hex number. Okay, generate bit streams to section. Okay, then program. Now this should work straight away when I'm programming. Where is the board? Here's the board. Program device. Bang. Yay, happy days. And now when I press reset, it stops. Okay, that's it. This is it. That concludes my video. I hope it was something to learn from, and I hope I shall see you in the next one.